In a control room somewhere in Hungary, in 2013, a team of astronomers were doing something that looked from the outside like simple counting. They were plotting gamma ray bursts on a chart, marking each one according to where in the sky it had appeared, building up a distribution map of the most energetic explosions the universe produces. Gamma ray bursts are brief, violent events, visible across billions of light years, and because they are scattered across cosmic time and space, astronomers had long assumed their positions in the sky would be roughly even, spread without pattern across the celestial sphere, like seeds thrown in all directions. What the team found, as the points accumulated on their chart, was that they were not spread evenly at all. In a particular region of sky lying between the constellations Hercules and Corona Borealis, the bursts were clustering. There were more of them than there should have been. There were far more of them than there should have been. The clustering was not subtle once the data were examined carefully. Across a span of sky that translated, at those distances, into something on the order of 10 billion light years, the excess of gamma ray bursts traced the outline of what appeared to be a coherent structure, a concentration of matter so large that naming it a wall felt almost inadequate, and yet wall was what the team reached for. The Hercules Corona Borealis Great Wall is not something anyone has seen. There is no photograph of it. No telescope has resolved its edges or measured its depth with direct observation. What exists is a pattern in the distribution of distant explosions, a shape that emerged slowly from the data, the way a figure emerges from static when stared at long enough. Though, in this case, the emergence was driven not by imagination, but by the patient application of statistics to a catalog that grew point by point over months of careful work. What made the discovery more than a curiosity was what it implied about the scale of the largest structures the universe contains. For decades, cosmologists had operated under a principle, sometimes called the cosmological principle, which holds that at the largest scales, the universe is broadly uniform. That matter, on average, is distributed without preferred direction or concentration when viewed at a grand enough resolution. The principle is not merely an assumption. It follows from well-established physics about how the universe expanded from its early state, and it is supported by the broad uniformity of the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, which is smoothed to roughly 1 part in 100,000. A structure 10 billion light years across does not sit comfortably inside that picture. It is, by the estimates of the astronomers who described it, too large to have assembled through any process the standard model of cosmic structure formation cleanly accounts for. The question the Hercules Corona Borealis Great Wall left open was not whether the structure exists, the statistical excess is real, but what it means for the models. Whether the structure is genuinely coherent, a single gravitationally related feature, or a line-of-sight alignment of unconnected overdensities at different distances remains a point of active examination. That uncertainty does not dissolve the shape in the data. It does not return the gamma ray burst distribution to smoothness. It simply means the shape is still being understood, its character still being established, its place in the inventory of what the universe contains still being assigned. The astronomers who found it did not claim to have solved anything. They reported what the map showed, and the map showed something unexpected. At scales somewhat smaller than the structures that challenge the cosmological principle, the universe has a character that astronomers have spent decades mapping and simulating and gradually coming to understand. The large-scale structure of the observable universe, seen across hundreds of millions and billions of light years, is not smooth. It is not even close to smooth. It is organized in the way a foam is organized, a three-dimensional mesh of thin walls and long threads and dense nodes, with enormous hollow regions occupying the spaces between them. The threads are filaments of matter, both ordinary and dark, along which galaxies tend to gather. The nodes at the intersections of those filaments are the densest concentrations in the visible universe, rich with galaxy clusters that contain hundreds or thousands of individual galaxies bound together by gravity. The hollow regions between the filaments are the voids, and they are genuinely nearly empty, at least by the standards of anywhere else the eye might fall in the cosmos. The image that supercomputer simulations of this structure produce is one of the quieter wonders in modern astrophysics. Rendered in false color, the cosmic web, which is what researchers call this architecture, simply and accurately looks like a three-dimensional mesh of faintly glowing threads, stretched between nodes that burn brightest at the densest intersections, with dark volumes that the mesh barely touches, filling the spaces between. The dark volumes are not entirely empty. Thin filaments of dark matter thread even through the quietest regions, invisible but structurally present, the lowest rungs of a scaffolding that continues well below the threshold of ordinary observation. The visible matter, stars, gas, galaxies, follows this scaffolding, because the scaffolding came first, its gravity drawing ordinary matter into the patterns we observe, and because the universe has had nearly 14 billion years for this gravitational herding to accumulate into the large-scale architecture seen today. The voids are the part of this structure that tend to hold attention most persistently. They are not rare or small. They are in fact the most common feature of the cosmic web by volume. The majority of the observable universe, measured simply as a fraction of space, is void, open regions where the density of ordinary matter is a small fraction of the cosmic average, where galaxies are sparse or entirely absent, where the large-scale filament structure simply does not reach in any meaningful way. The existence of such regions is predicted by the same models that describe the filaments and clusters, and in that sense they are not anomalous. They are what structure looks like when it concentrates. The gaps are the direct complement of the concentrations, the emptiness that is the flip side of the density found in clusters and walls. One particular void became famous in astronomical circles in 1981 when a survey of galaxy positions in the direction of the constellation Boötes returned an unusual result. In a roughly spherical region, approximately 330 million light-years across, the survey found very few galaxies. Statistical models predicting the expected number of galaxies in a volume of that size suggested the region should contain something on the order of thousands of them. The actual count at the time was closer to 60. The Boötes void as it came to be called after the constellation toward which it lay in the sky, was not discovered through absence in any intuitive sense. It was discovered by noticing that a catalog of galaxy positions had a gap in it, a region where the expected entries were simply not present. The 60 or so galaxies found within the Boötes void are not scattered randomly through its interior. They tend to be concentrated along a loose filament or sheet arrangement even within the void itself, as though the process of structure formation has continued at a very faint level even in a region most matter has vacated. This internal structure is consistent with the idea that voids are not perfectly empty. Dark matter filaments are thought to persist even within them, providing a very weak gravitational skeleton for the small number of galaxies that remain, or that perhaps formed there slowly in conditions of unusually low density. The void's edge is also not perfectly sharp. The transition from void interior to the denser shell of galaxies surrounding it happens over a range of distances, a gradient rather than a hard boundary, which is also consistent with how the simulations describe void boundaries at this scale. What the Bodit's void makes concrete, in a way that is difficult to arrive at through numbers alone, is the scale of emptiness the universe maintains as a structural feature. A sphere 330 million light-years across is a volume inside which many thousands of galaxies, each containing hundreds of billions of stars, are simply absent. If the solar system had formed inside the Bodit's void rather than in the Milky Way, which formed as galaxies do, along a filament, the night sky would have contained almost nothing. The nearest galaxy to a hypothetical observer there would have been far more distant than Andromeda is from Earth. The darkness would have been deeper, the sky more uniform, the evidence of a larger structured universe much harder to gather. The fact that the night sky is as rich as it is, in galaxies visible to telescopes, and in the smear of the Milky Way visible to the naked eye, is a consequence of where the solar system happened to form, in a well-populated region of a well-populated filament, in a universe that is elsewhere much more sparsely furnished. The Sloan Great Wall came into view in a different way. Rather than emerging from the distribution of gamma-ray bursts, or from a gap in a galaxy catalog, it emerged from the positive presence of galaxies themselves, specifically from the patient accumulation of galaxy positions in the Sloan Digital Sky Survey, an effort that began systematically mapping the sky in the late 1990s and by 2003 had assembled a three-dimensional catalog of galaxy positions substantial enough to reveal, when examined statistically, a concentration stretching across approximately 137 billion light-years. The Sloan Great Wall was identified not by eye. No single astronomer looked at a map and saw it directly, but by applying measures of clustering to position data and watching a coherent overdensity emerge from the numbers, the way a shape emerges in a pointillist painting when the viewer steps back far enough for individual marks to give way to contour. The Sloan Great Wall is a filament in the cosmic web, a dense concentration of galaxy clusters and superclusters assembled along the axis of a dark matter filament over billions of years of gravitational accumulation. It is not the largest structure known, the Hercules Corona Borealis Great Wall, and several other candidates identified since exceed it, but it was, at the time of its identification, the largest structure then catalogued, and it held that distinction for several years before larger candidates were established. Its length, approximately 137 billion light-years, means that light traveling at its constant 300,000 kilometers per second would take over a billion years simply to cross it end to end, which is itself a figure that tends not to mean much until it is compared with something more immediately imaginable. The entire observable universe is only about 93 billion light-years across in its current extent, and the Sloan Great Wall spans a noticeable fraction of that distance as a single coherent feature in it. The process that built the Sloan Great Wall, and that builds all the walls and filaments of the cosmic web, began very early in the history of the universe, far earlier than any galaxy existed. In the first fraction of a second after the Big Bang, the universe was a nearly uniform sea of energy and elementary particles, with only the faintest variations in density from one region to the next. Those variations, quantum fluctuations amplified to cosmic scale by the rapid expansion of the early universe, were the seeds from which everything grew. The slightly denser regions attracted matter gravitationally. Matter flowed along the paths of least resistance between slightly denser regions, accumulating where density was highest, draining away from regions where it was lowest. Over hundreds of millions of years, and then billions of years, This process amplified the initial tiny fluctuations into the large-scale structure visible today. The web of filaments and voids, the clusters and walls, the vast near-empty spaces, and the dense concentrations sitting at their edges. The material that organized first and most effectively along these paths was not ordinary matter, it was dark matter, which does not interact with light, does not form stars or planets, does not produce any electromagnetic signal that any instrument built so far has detected. Dark matter constitutes approximately 27% of the total mass energy content of the universe, more than 5 times the mass of all the ordinary matter that exists in stars and gas and dust and planets combined. Its presence is inferred from its gravitational effects, which are extensive and consistent and reproducible. The rotational curves of galaxies, the way stars in the outer regions of disk galaxies orbit at speeds that require far more mass than the visible stars and gas can account for, point clearly to large quantities of additional mass distributed in extended halos around those galaxies. The motions of galaxies within clusters, the gravitational lensing of background objects by those same clusters, and the detailed structure of the cosmic microwave background all independently require a large component of matter that contributes mass without contributing light. Because dark matter responds to gravity, but not to the electromagnetic force that governs ordinary matter, it began clustering earlier in the history of the universe. And ordinary matter in the early universe was coupled to photons. It interacted strongly with light, and the pressure of the radiation field prevented it from collapsing under gravity for a long period. Dark matter had no such constraint. It began forming gravitational wells from the earliest stages, pulling into concentrations that grew steadily deeper even while ordinary matter was still held smooth by radiation pressure. When ordinary matter finally decoupled from the photon field, roughly 380,000 years after the Big Bang, the moment whose echo is the cosmic microwave background, it found a pre-existing framework of dark matter concentrations waiting for it. It fell into those concentrations. It followed their geometry. The first galaxies formed inside the deepest dark matter wells, and the filamentary structure of the cosmic web reflects the shape that dark matter had already established before a single star existed anywhere in the universe. This means that the architecture of everything visible in the night sky, every galaxy, every cluster, every great wall and filament, was pre-shaped by something that no instrument has photographed. The cosmic web exists because dark matter assembled its own version of it first, and ordinary matter had no choice but to follow the paths that the invisible scaffolding had already laid out. When astronomers map the positions of galaxies and identify the large-scale structure of the universe, they are in a sense tracing the outline of a form that was there before the galaxies were, a form whose full detail remains unknown because it cannot be directly observed, only inferred from the positions and velocities of the things that fell into it. The 2003 identification of the Sloan Great Wall and the 2013 detection of the Hercules Corona Borealis Great Wall were both, in this sense, acts of tracing an outline. The galaxies that define the walls are markers of a deeper structure. Their positions point to concentrations of dark matter that cannot themselves be located on any map made with optical light. The visible universe is an annotation on an invisible architecture, and the annotation is the part that all the instruments so far built can read, rich, detailed, and remarkable, but not the whole document. The scale at which the cosmic web operates is not easy to hold in mind as a single image. Moving from the Hercules Corona Borealis Great Wall at 10 billion light-years down to a single galaxy cluster, sitting at one of the web's nodes, involves crossing several orders of magnitude, and doing it in a single sweep tends to lose the character of each level. One way to keep the structure from becoming merely numerical is to stay with a specific part of it. To take the Bhuta's void, for instance, and remain inside its 330 million light-year sphere long enough to understand that its emptiness is not random or temporary, but is a structural feature, a persistent characteristic of that region of space, the result of matter having evacuated it over billions of years, as gravity drew material toward the surrounding filaments and left the interior progressively more sparse. The evacuation of a void is not a rapid process. It takes the entire age of the universe to produce a void of the depth and size of Botti's, and even after that time, the process is not complete. Matter is still moving, the void is still slowly deepening, the walls surrounding it are still slowly accreting the material that drains from its interior. The universe's large-scale structure is not a static picture. It is a process, still unfolding, still building toward configurations that will look different in a billion years than they do today. The walls will be denser, the voids will be emptier, the filaments will be more defined. The web is tightening very slowly, and it will continue to tighten until the accelerating expansion of the universe, driven by whatever dark energy is, begins to overpower the local gravitational forces that are drawing things together, at which point the story of large-scale structure will enter a phase that even the current models do not agree on in detail. Dark energy, which accounts for approximately 68% of the total mass energy content of the universe, is the component least well understood of the three major constituents. Ordinary matter and dark matter both make intuitive sense as things that exist in space and have mass. Dark energy is a property of space itself, or is consistent with being such a property, a gentle outward pressure that increases in total effect as the universe expands, because more space means more of whatever dark energy is, which means more outward pressure, which means faster expansion. The current observational evidence is that the expansion of the universe is accelerating, and the most straightforward accounting for that acceleration is a uniform dark energy filling all of space with a constant density. The large-scale structure of the universe sits inside this expanding, accelerating frame, its local gravitational binding competing quietly with the broader tendency of everything to move apart, filaments and clusters holding their shape where gravity wins and the voids between them widening where dark energy has the upper hand. What the cosmic web represents, taken as a whole, is the record of a competition that has been running for nearly 14 billion years. Gravity pulling matter together, early radiation pressure holding it apart, dark energy pushing space outward, dark matter front-running the assembly of structure in the periods before ordinary matter could collapse freely. The large-scale structure visible today is the current state of that competition. Not an equilibrium, not a final form, but a snapshot of a process at a particular point in its evolution. The Hercules Corona Borealis Great Wall is a snapshot. The Bautis Void is a snapshot. The Sloan Great Wall, curving through hundreds of millions of parsecs of space, is a snapshot. Each one is a feature of a universe still very much in motion, its architecture still changing on the timescales relevant to cosmological dynamics. The structures that seem solid and established from a human perspective being, at cosmic timescales, as impermanent as weather patterns viewed from an appropriately elevated distance. The nodes of the cosmic web, the densest intersection points where multiple filaments converge, contains some of the most massive concentrations of matter in the observable universe. A rich galaxy cluster at one of these nodes might contain hundreds of individual galaxies, each with its own hundreds of billions of stars, all bound together within a common envelope of hot gas and an extended dark matter halo. The hot gas in such a cluster, heated to temperatures of tens of millions of Kelvin by the kinetic energy of infalling matter over billions of years, glows in X-ray radiation bright enough to be detected across enormous distances. The dark matter halos surrounding galaxy clusters can be mapped by observing how light from background galaxies is bent and distorted as it passes through the cluster, a phenomenon called gravitational lensing, which turns a galaxy cluster into a natural telescope of sorts, bending the paths of light rays from objects behind it in ways that depend precisely on the mass distribution of the cluster itself. Through gravitational lensing maps of galaxy clusters, astrophysicists have produced images of the dark matter distribution in clusters that show it extending well beyond the visible boundaries of the galaxies and gas, surrounding the whole system in a smooth, extended halo that encompasses but vastly exceeds in volume the bright stuff at the center. These maps are among the closest thing to a direct image of dark matter that currently exists, not an image of dark matter itself, which remains undetected by any direct instrument, but an image of the distortion pattern it imposes on the light of background galaxies, which can be processed into a mass map that shows where the dark matter must be for the observed distortions to occur. The shape that emerges from such a map is a smooth, roughly spherical halo, concentrated toward the cluster center, but tapering gradually out to edges that blend into the surrounding cosmic web structure. The filaments themselves, the long threads that connect cluster nodes and define the large-scale architecture of the cosmic web, are harder to observe directly than the clusters at their intersections. The density of matter in a filament is much lower than in a cluster, and the gas inside filaments, while warm enough to emit some radiation, is faint enough that detecting it requires careful stacking of many observations or the use of instruments sensitive to the specific wavelengths it emits. Direct detections of individual filaments using X-ray telescopes and through their effect on the cosmic microwave background have been reported in recent years, and the observational evidence for the filamentary structure predicted by dark matter simulations has grown considerably more direct over time. The cosmic web is no longer simply inferred from galaxy distributions and supercomputer models. Pieces of it have been measured directly, their temperatures and densities estimated, their gas content probed. The fraction of ordinary matter residing in these filaments rather than in galaxies and clusters is itself an interesting question. For some time, estimates of the total ordinary matter content of the universe, based on nucleosynthesis, the way light elements formed in the first minutes after the Big Bang, were higher than the total mass found in observed stars and galaxies, leaving a gap sometimes called the missing baryons problem. The leading candidate location for the missing baryons was always the cosmic web filaments, a warm, diffuse intergalactic medium threading through the web at temperatures between 100,000 and 10 million Kelvin, bright enough to be significant, but faint enough to be difficult to detect. Observations over the past decade have produced increasing evidence that a substantial fraction of these missing baryons do indeed reside in the filaments, slowly closing the accounting gap between what physics predicts should be there and what the instruments have so far found. All of this, the great walls, the voids, the filaments, the cluster nodes, the dark matter halos, the missing baryons slowly being found in the warm gas of the cosmic web, was assembled from conditions that were, in their origins, extraordinarily uniform. The fluctuations in density that seeded the whole structure were, in the early universe, tiny fractions of a percent. The smooth sea of energy that existed in the first instance left very little room for the development of what would become, billions of years later, walls 10 billion light years long and voids 330 million light years wide. The amplification of those tiny initial variations by gravity over the full age of the universe is the process that produced everything the cosmic web contains. It is a process of patient, impersonal accumulation, gravity working on density differences no larger than the ripple of a very quiet wave, given all the time that existed, building structures whose scale exceeds anything that can be walked around or pointed to or seen with an unaided eye. What remains unknown about this architecture is substantial. The exact nature of dark matter, what particle or field it consists of, whether it interacts with ordinary matter in any way beyond gravity, whether it is truly cold and slow-moving or has some warmth and pressure of its own, remains an open question despite decades of experimental effort. The properties of dark energy, and whether it is truly a constant of the vacuum or varies with time, will change the predicted future of the large-scale structure in ways that current observations cannot yet resolve. The full extent of the largest structures, whether the Hercules Corona Borealis Great Wall is genuinely coherent, or whether still larger patterns exist beyond the current survey boundaries, is limited by the size of the observable universe itself, the sphere beyond which light has not had time to reach us, and which therefore contains no information the instruments can access. The observable universe, that 93 billion light-year sphere centered wherever the observer stands, is itself a kind of boundary condition on what any instrument can find. The structures inside it are the structures that can be mapped. What lies beyond, whether more walls and voids or something entirely different, is not accessible to any observation from within. The cosmological principle, the idea that the universe is broadly uniform at the largest scales, may hold well beyond the observable boundary, making the universe beyond it look much like the part inside it. Or the universe may extend in ways that differ from the observable region. There is currently no way to know. The maps end where the light runs out, and the architecture of space beyond that edge belongs to theoretical speculation rather than to observation. Every galaxy in every photograph taken by every telescope is located within a dark matter halo, embedded in a filament or node of the cosmic web, sitting at a specific point in the large-scale structure that dark matter laid out before the first star ignited. The Milky Way is itself a moderately large spiral galaxy, sitting in a region of the cosmic web called the local group, which lies near the edge of a larger structure called the Virgo supercluster, which is itself now understood to be a tendril of an even larger structure called Laniakea, a supercluster spanning roughly 520 million light-years, whose name, drawn from Hawaiian, means immeasurable heaven. The galaxy is located, in other words, in a specific place, in a specific filament of a web that extends in every direction for billions of light years, most of it dark, most of it invisible to every instrument that detects light, its full shape known only in the approximate outlines that gravity's effects allow to be inferred. The dark matter scaffolding that underlies all of this has never been directly photographed. No instrument has produced an image in which dark matter particles are the source. The gravitational lensing maps show where it must be, and the rotation curves of galaxies show how much of it each galaxy must contain, and the clustering statistics of galaxies trace the geometry of the web it forms. But these are all observations of the effects of dark matter, not of dark matter itself. The scaffolding is known entirely through the behavior of the things sitting inside it, the way a structure can sometimes be known entirely from the shapes of the objects it supports, without any direct view of the beams and joints that hold everything in place. The galaxies that fill every long exposure photograph of the deep sky, the tens of thousands visible in the Hubble Ultra Deep Field, each one a system of hundreds of billions of stars, are all sitting inside structures no instrument has ever directly photographed. They are annotations on an invisible architecture, their positions and velocities and clustering patterns, the only direct evidence that the architecture exists. That evidence is consistent, reproducible, and now well enough established that the existence of the dark matter web is not seriously doubted in the relevant scientific communities. The architecture is real. It is there. It is simply not made of anything that light, in any part of the electromagnetic spectrum so far explored, can find and return an image of. And so the universe's largest structures remain, for now, readable only in the way something can be read when the text is absent, but the impression it left remains, in the arrangement of the things that followed it, settled into the shapes it determined, distributed across billions of light years, in patterns that reflect a scaffolding assembled in the universe's first 100 million years, long before there was anyone to notice it taking form, and long before any telescope existed to record the shapes it left behind in the quiet placement of the galaxies still drifting slowly, imperceptibly, along the lines it drew. In 1975, a camera opened on the surface of another planet for the first time. The image that came back showed rocks, not dramatic formations or towering cliffs, just rocks sitting on flat ground lit by a filtered orange light that came through 65 kilometers of thick atmosphere above them. The edges of the rocks were sharp. They had not been worn smooth by wind or water. They were basaltic, angular, freshly exposed by some ancient geological event, and they sat there on the surface of Venus in the particular stillness of a place where nothing had disturbed them for a very long time. The photograph existed briefly on a screen in a Soviet control room, was transmitted, and then the probe that had taken it stopped working. The surface of Venus, at approximately 465 degrees Celsius, and with atmospheric pressure 90 times that of Earth at sea level, does not allow spacecraft to operate for long. Venera 9 lasted 53 minutes on the ground before the heat overcame it. In those 53 minutes, it returned the first ground-level photograph ever taken on another planet. The Venera program was the Soviet Union's long effort to reach Venus, and it had been running for over a decade before that first successful surface image. Several earlier probes had been crushed by the pressure before they could transmit anything. Others had been lost in transit. The program involved careful adjustments to heat shielding, pressure casing, and transmission timing, each new probe incorporating what the previous failure had taught, in the way that all systematic exploration tends to work. Venera 9 was the first to carry a camera with a clear field of view. It was the first to confirm that the Venusian surface was not a soft, deep dust landscape as some models had predicted, but a place of solid, textured rock sitting in the thick orange light that filtered down from a sky no human eye had ever seen. Over the following 9 years, 9 more Venera probes successfully reached the Venusian surface and returned data. Venera 13 survived the longest, operating for 127 minutes and returning the first color photographs from the surface. The same sharp rocks in the same amber light, rendered now in the warm tones that gave the Venusian surface its particular quality of looking both alien in some way that was harder to explain, almost geological in a familiar sense. The rocks looked like rocks. They looked like something from a high desert at dusk. The color of the light did that. The Soviet engineers had built cameras with color calibration charts attached to the lander body so that the hues in the images could be corrected against a known reference. Those color charts are visible in the photographs, sitting at the edge of the frame, surrounded by Venusian rock, in a detail that is easy to overlook and rather pleasant once noticed. No spacecraft has successfully operated on the surface of Venus since Venera 14 in 1982. Proposals for new landers have been drawn up, revised, and returned to for study in the decades since. The engineering challenge remains exactly what it was when the Soviet scientists were working on it. The surface of Venus destroys what lands on it, and the window for returning data is measured in minutes. The photographs Venera 9 through 14 returned are still the most detailed ground-level images of the Venusian surface that exist. In a catalog of planetary exploration achievements that spans more than 6 decades, that is a notable fact that a program which concluded in 1984 still holds in one particular category the record. There is a spacecraft launched in 1978 that, for a certain stretch of years, no one was listening to. IC-3, the International Sun-Earth Explorer 3, was designed to study the solar wind from a position between Earth and the Sun. It operated for years in that role, then was repurposed in the mid-1980s to study 2 comets, including Halley's Comet on its 1986 return, and then was formally retired. NASA decommissioned it in 1997, meaning that after that date, no one was routinely monitoring its transmissions. The spacecraft itself, of course, did not stop. It continued on its orbital path around the Sun, making a slow return arc that would bring it back near Earth. Its transmitter was still working. Its instruments were still drawing power from its decaying nuclear source. It was a functioning spacecraft, in the sense that it continued to exist and operate, just one that no one was listening to. In 2013, a group of engineers, scientists, and space enthusiasts learned that IC-3 would make its closest approach to Earth in 2014, passing near the Moon. The window for contacting it would be brief. NASA did not have the equipment or the allocated resources to re-establish contact. The transmitter dish that had originally been used to communicate with IC-3 had been modified for other purposes. The hardware required to speak to a probe of that era was, in some respects, easier to rebuild than to find. A crowdfunding campaign raised over $150,000. A team assembled at the Arecibo Observatory in Puerto Rico using a combination of repurposed radio equipment and software-defined radio techniques that would have been impossible in 1978, and they pointed their antenna at the coordinates where the probe should be. The signal came back. IC-3 answered. Its telemetry was readable. Its instruments were returning data. After years of traveling in unmonitored silence, it was still functional enough to respond to a command. The team successfully uplinked new instructions to the spacecraft in an attempt to fire its thrusters and adjust its trajectory, but the attitude control propellant had been exhausted and the maneuver could not be completed. The probe continued on its original path. What the operation demonstrated, and what, though, was the narrowness of the gap between lost and found, that a spacecraft declared decommissioned could be reached again by a small team with equipment that had not existed when the probe was built, using a radio telescope in Puerto Rico on a short window in the summer of 2014. IC-3 made its closest pass to Earth that August and continued outward again. Its signal became harder to detect as the distance increased. The team monitored it as long as the signal was receivable, and then let it go. The probe is still out there, still orbiting the sun, on a long elliptical path that will return it in approximately 17 years. The Israeli spacecraft Bereshit was launched in February 2019, the first privately funded lander to reach lunar orbit. The mission had been built by Space.il, an Israeli nonprofit that had originally entered the competition known as the Google Lunar XPIs, and then continued development after the prize deadline passed without a winner. Bereshit was small, about the size of a washing machine, and carried a modest instrument payload along with a time capsule and a copy of Wikipedia on a nickel disc. It also carried, almost as a quiet footnote to the main mission, a sample of tardigrades in a state of suspended desiccation. The descent to the lunar surface went wrong in stages. A sensor failure caused the main computer to reset during the braking sequence, and the engine cut out at an altitude where it could not be safely restarted in time. Mission Control in Tel Aviv watched the telemetry as the spacecraft's velocity stopped decreasing when it should have been nearly zero. Bereshit impacted the Mare Serenitatis region, the Sea of Serenity, at a speed that destroyed the spacecraft on contact. The signal went quiet. The photographs Bereshit had taken during its approach and partial descent were already transmitted and safely archived. The mission had, in some real technical sense, accomplished a significant part of what it set out to do. It had reached the moon, had entered orbit, had returned data, had demonstrated what a small private mission with a limited budget could achieve. The landing itself, the final 15 minutes of a journey, months in the making, had not worked out as planned. What remained on the lunar surface, somewhere in the debris of the impact zone, was a small container of tardigrades. Tardigrades, in their desiccated form, are essentially inert, not quite alive in any active metabolic sense, but not dead either, in a way that resists the usual categories. They can survive, in that state, conditions that would be fatal to almost any other living thing. Whether any survived the impact and what the lunar environment does to them over time remained genuinely unresolved after the crash. Lunar conditions, hard radiation, vacuum, extreme temperature swings, are not kind to organic material, but the tardigrades' particular biology gives them a documented resilience that makes the question, at minimum, worth asking. No follow-up mission has visited the site. The container sits wherever the debris settled, in a crater on a gray plain, with Mare Serenitatis spread out around it in the quiet. The ExoMars 2016 mission launched with 2 spacecraft, the Trace Gas Orbiter, designed to study the Martian atmosphere from above, and Schiaparelli, a lander whose purpose was specifically to test the entry, descent, and landing technologies that ESA would need for future Mars missions. Schiaparelli was not primarily a science lander. It carried instruments, and it would have returned useful atmospheric data had it landed successfully, but its central purpose was the demonstration to show that the sequence of events required to put hardware safely on the Martian surface could be executed reliably. The events of October 19, 2016, when Schiaparelli entered the Martian atmosphere, went wrong at a specific and diagnosable point. The inertial measurement unit, the system responsible for calculating the lander's orientation and motion, saturated during the descent. This is a technical term for what happens when a sensor is asked to measure something larger than its measurement range. It pegs at its maximum value and holds there, as if the measured quantity has stopped changing, even when it has not. The saturation lasted only a second or so. It was a brief anomaly in the data, but in that second, the lander's onboard computer was running a model of the descent, and the model was dependent on the sensor data. With the sensor pegged at its maximum reading, The computer calculated that the vehicle had already reached the surface. It concluded the landing was complete. Based on that conclusion, the parachute was released early. The retro rockets were fired for a fraction of their intended duration, approximately 3 seconds instead of the planned 30 seconds or more, and then shut off. The ground clearance at that point was 37 kilometers. Schiaparelli fell the remaining distance without deceleration, striking the surface at over 300 kilometers per hour and leaving a dark impact scar on the Martian plain that was photographed from orbit by NASA's Mars Reconnaissance Orbiter 2 days later. The scar was small, approximately 4 by 5 meters, but clearly visible from above. ESA was able to reconstruct the sequence of events precisely from the telemetry data that had been transmitted in real time to the trace gas orbiter before contact was lost. The failure was complete, and it was legible, which in engineering terms is a meaningful distinction. A failure whose cause is known can be corrected. The trace gas orbiter continued its work above Mars. It entered its operational orbit the following year and began returning atmospheric data. The mission, considered as a whole, produced a functioning orbiting science platform and a very detailed record of what goes wrong when an onboard navigational model encounters sensor saturation during atmospheric entry. Both of those things had value, though in different proportions than the mission team had planned. Soviet planetary exploration in the 1980s included 2 ambitious missions to Phobos, the larger of Mars's 2 moons. Phobos 1 and Phobos 2 were launched in July 1988, 5 days apart, both intended to rendezvous with the small, irregularly shaped moon and deploy landers to its surface. The Phobos program represented a significant investment and genuine scientific ambition. Phobos is one of the odder objects in the solar system, a body whose origin is not fully agreed upon even now, and landing instruments on it would have been a considerable achievement. Phobos 1 did not reach Mars. The loss came through a command sequence uploaded from the ground. In August 1988, a ground controller at the Soviet mission facility was using a computer terminal to prepare commands for the spacecraft. The software being used did not have adequate error checking for the command parameters being entered. A sequence was uploaded that included an incorrect instruction, one that disabled the attitude control thrusters. Without its attitude control thrusters, the spacecraft could not maintain the orientation of its solar panels toward the sun. The solar panels drifted out of alignment. Over the following hours, the batteries deprived of their charging source discharged. When the batteries were empty, the spacecraft had no power. No further signal was received from Phobos 1. The error was identified after the fact, traced to the command sequence, and attributed to a procedural gap rather than any failure in the spacecraft's hardware. The spacecraft was in good working order when the command was sent. It simply could not respond to the instruction it had been given and survive. Phobos 1 is still in interplanetary space. It did not have the velocity to leave the solar system, and it did not have the trajectory to fall into the sun or to reach another planet. It is orbiting the sun somewhere in the inner solar system, following a path that was established in 1988 and has not been significantly altered since. It has no power. Its instruments are silent. There is nothing aboard it transmitting, nothing receiving. It is, in the concrete physical sense, simply a metal object following a gravitational arc, as objects in space do, without adjustment and without end. The human dimension of that, of the controller who entered the wrong command, of the ground team who sent the sequence and waited for a response that never arrived. of the engineers who had spent years designing a mission to a moon that their spacecraft would now never reach, belongs to the story, but the story is as much about what the spacecraft does as about what the people did. What the spacecraft does is continue. It travels the path it was set on. It carries no memory of what it was built for, no record of the mission objectives it was designed to fulfill. It is a fact of orbital mechanics that objects in stable solar orbits remain in those orbits for a very long time, absent some large perturbation. Phobos 1 will be somewhere in the inner solar system for a very long time indeed. Phobos 2 reached Mars and actually began studying Phobos itself, returning a limited number of images and thermal readings of the moon's surface. Contact was lost in March 1989 during an orbital maneuver before the planned Phobos landing. The cause was traced to a software issue in the onboard computer. The data it returned before contact was lost, added to the picture of what Phobos looks like from close range, a lumpy, dark, cratered object moving in a low orbit around Mars, with surface features that raised questions about its composition and origin. Those questions remained open when contact was lost, and they remained open in the years that followed, answered only partially by other spacecraft that observed Phobos from a distance while on their way to study Mars itself. There is something worth pausing on in the specific texture of that era of space exploration, the late 1970s through the late 1980s, when the ambitions of the programs had outrun, in certain respects, the reliability of the tools. Commands sent from Earth to spacecraft could not be recalled once transmitted. Software running onboard computers could not be updated in the way that modern spacecraft software can be patched from the ground. The margin for error was narrow in ways that were, in some cases, not fully appreciated until an error exposed them. The Venera program succeeded through the accumulation of careful physical engineering, building the probe to survive what was already known to be a brutal environment, and measuring the success in minutes of operation rather than years. The IC-3 and Phobos programs operated in a different environment, one where the spacecraft could be spoken to and commanded, and where that very capability introduced a vulnerability that a simpler, more autonomous probe did not have. The citizen scientists who recontacted IC-3 in 2014 were working with a much wider set of tools than the mission's original engineers had. Software-defined radio, the technology that allowed a standard computer to handle signal processing that once required dedicated hardware, made certain things achievable in 2014 that would have been practically impossible in 1978. The team could listen at frequencies and resolutions that ground stations of the original era could not have managed with off-the-shelf equipment. In a narrow technical sense, the gap between a decommissioned probe and a functioning one had shrunk. The spacecraft had not changed. The tools for reaching it had been. Bersheet carried tardigrades because a private organization called the Arch Mission Foundation had partnered with Space.il to include what it described as a lunar library, a collection of human knowledge archived on durable media intended as a long-term record in case something needed preserving. The tardigrades were added as a biological sample, part of a broader archive that also included human DNA profiles and the text of various human documents. The inclusion of living organisms, even in their desiccated, biologically suspended form, in an unplanned lunar deposit, raised questions afterward about planetary protection protocols, which govern what biological material may be introduced to bodies in the solar system. The moon is not considered a priority protected body under those protocols, but the principle that landing organic material on another world should be intentional and considered is the kind of principle that a crash landing complicates. The container is small, the tardigrades within it if any survived, are extraordinarily small. Individual tardigrades are measured in fractions of a millimeter, visible under a moderate microscope, but not to the unaided eye. They are sitting in debris on a lunar plain in conditions that have not been measured at the site of the wreck. The question of what happens to a tardigrade on the lunar surface over time, years, decades, the slow accumulation of cosmic ray exposure, and the deep swing of temperature between lunar day and lunar night, is one that existing data can partially address but cannot fully resolve. They are not likely to thrive. Whether they remain in any meaningful sense of the word preserved, in the way that desiccated tardigrades on Earth can sometimes be rehydrated after decades and return to activity, is a question whose answer requires being there to check. None of the missions in this chapter ended exactly where they were planned to end. This is, in retrospect, an unremarkable observation. The history of spacecraft is a history of iterations, and the iterations that go wrong are as instructive as the ones that succeed, sometimes more so. The ESA engineers who analyzed the Schiaparelli telemetry data produced a report that ran to considerable detail about the specific sequence of sensor saturation, model error, and premature actuation that caused the crash. That report existed because the trace gas orbiter had received and stored the telemetry from Schiaparelli during descent. The decision to relay that data in real time and to build the orbiter's communication systems to handle it meant that when the landing failed, the failure was fully documented. What was lost was the lander. What was preserved was the account of why. The Soviet engineers who worked on the Venera program through the 1960s and 1970s had no certainty at each launch that their probe would survive to the surface. The first landers to reach Venus were destroyed before they could transmit any images. The pressure at the surface was far higher than early models had estimated, and the early spacecraft were not built to survive it. With each new probe, the engineers revised their understanding and adjusted the hardware, adding pressure tolerance incrementally until, with Venera 9, they had something that not only survived but operated long enough to return a photograph that had never been taken before. Those sharp angular rocks in orange light were the result of accumulated redesigns, each one informed by a failure that had happened before it. The spacecraft sent between 1978 and 1989 were, in different ways, all navigating the edge of what was technically achievable at their moment. IC-3 was asked to do something, fly to a comet that had not been part of its original design requirements. Phobos 1 and 2 were part of a program attempting to land on a body that had never been visited up close. Beresheet was a small private mission attempting something that only 3 national agencies with decades of institutional experience had managed. The Schiaparelli lander was specifically designed to discover the failure modes that would matter for future missions, and it discovered several of them in a very final way. All of them are still out there, in one form or another. The Venera probes are on the surface of Venus, slowly being chemically eroded by an atmosphere that dissolves most metals. IC-3 is in its solar orbit, completing another slow loop. The Beresheet wreckage is on the floor of Mare Serenitatis. Schiaparelli is a small dark stain on an ochre Martian plain, and Phobos 1 is somewhere in the inner solar system, on a path it has been following since the summer of 1988, carrying no signal, offering nothing, just moving as things in space move when there is nothing acting on them, and nowhere in particular they are going. The image that holds is that one, not the photographs from Venera 9, which were a success and have a brightness about them. not the crowded room of engineers in Puerto Rico listening for a signal that came back, which has a particular warmth to it. The image that lingers is simpler than both of those. Phobos 1, tumbling slightly perhaps, or perhaps not. There is no way of knowing its rotation now, moving in its long, slow arc through the inner solar system, past the orbit of Mars on one side and back toward Earth on the other, year after year after year. Its mission ended in the first 2 months. Its journey did not. The solar wind presses against it with the same faint pressure it exerts on everything in this neighborhood of space. The sun's gravity holds it in its path with the same authority it holds all the other objects circling here, large and small, dead and active, intended and accidental. There are other probes in similar conditions, spacecraft that have been lost, decommissioned, or outlasted their missions and continue in orbital silence. The solar system's inner region contains a quiet population of these objects, things that were built with great care and sent with specific intentions and are now simply following the mathematics of their trajectories. They will do so for a long time. Gravity is patient in that way. The path that was set in 1988 continues to be followed in whatever year this is now, and will be followed in years to come, with the same unvarying precision that makes orbital mechanics reliable enough to trust with spacecraft in the first place. Phobos 1 drifts on. Not lost in any absolute sense, its position can be estimated from its known launch trajectory and the time elapsed since contact was lost. Not traveling toward anything in any purposeful sense, the path it is on does not lead to Phobos or to Mars or back to Earth in any useful way. It is simply continuing. The solar system goes about its ordinary business around it, planets moving in their lanes, smaller bodies in their own varied orbits, and Phobos 1 among them, following the path it was given, carrying only its own weight through the long and unhurried dark. Deep inside Neptune, far below any layer a probe has ever reached, there is no light, there is no light, and there is no sound that anything alive could hear, and the pressure there is millions of times greater than the weight of the atmosphere resting on the surface of the Earth. Carbon atoms, under conditions that cannot be directly measured from the outside, are being pressed into geometric arrangements, crystalline lattices forming in the dark, solid and precise, at temperatures approaching several thousand degrees. In laboratory experiments using laser-driven shock waves, researchers have reproduced the conditions they believe exist in those interiors, and what the experiments produced, briefly and at enormous energy cost, were diamonds. The diamonds forming inside Neptune are not being formed for any purpose. They fall slowly toward the core once they condense, sinking through layers of ice and fluid that would not resemble ice in any way a person standing on the surface of the Earth would recognize. The process continues without interruption, in total darkness, at a depth that no instrument has ever directly visited and probably never will. What makes this image worth holding on to is how completely it asks to be imagined rather than seen. Everything known about the diamond rain inside Neptune and Uranus comes from working backward, from understanding the chemistry of carbon at extreme pressure, from running the laser experiments, from modeling what the pressures inside ice giant interiors must be. No photograph has captured it. No probe has descended into it. The knowledge exists entirely in inference, in the logic of physics applied to conditions that have only been approximated, never replicated at true scale. And yet the inference is solid. The process is almost certainly happening. Diamonds are almost certainly falling, slowly, in the dark, inside planets that appear from the outside as calm blue-green spheres drifting in the outer solar system. That is what the experiments say. That is what the models support. Uranus and Neptune are close enough in their internal structure that the same process is expected to occur in both, though the details differ slightly. Both planets carry a high proportion of carbon in their deep interiors. Both reach the pressures and temperatures required. Both have been described in planetary science as ice giants, a term that is somewhat misleading. The ices inside them are not frozen in the way the word usually implies, but are instead highly compressed, electrically conductive mixtures of water, ammonia, and methane under conditions that alter their behavior well beyond anything familiar. The carbon in those mixtures, compressed far enough, crosses into something else entirely. The diamonds that form are not large. Estimates suggest centimeters rather than meters, but they are forming continuously over the entire deep interior of worlds wider than 30,000 kilometers. The scale of the process, considered quietly, is enormous. Farther from the solar system, in a region far beyond the reach of any current mission or instrument, conditions grow stranger still. HD 189733b orbits a star approximately 64 light-years from Earth, and what makes this planet worth considering is not its distance, but its sky. The atmosphere of HD 189733b contains silicate particles, the same class of material that makes up sand and glass on Earth, suspended at high altitude and driven around the planet by winds measured at several thousand kilometers per hour. Those particles scatter light in a way that gives the sky of this planet a deep cobalt blue, a color produced not by the presence of water or nitrogen, as it is on Earth, but by the physics of tiny glass particles interacting with starlight at extreme velocity. The planet is a hot Jupiter, a gas giant so close to its star that it completes one orbit in about 2 Earth days, and the heat on its day side is enough to keep most metals in a gaseous state. The winds on HD 189733b move at speeds that make any weather system on Earth look essentially still. 8,000 kilometers per hour is a figure that requires some translation to feel. It is roughly 10 times the speed of the most intense surface winds ever recorded on Earth, sustained globally and continuously, carrying not rain or snow, but sharp silicate particles across the surface of a planet where nothing solid exists to impede them. The glass particles do not fall downward toward a surface. They are carried horizontally across the face of a planet that has no surface in the way that word usually applies, just layers of gas deepening under pressure, the particles cycling through a weather system the size of a world. In the cooler regions of the upper atmosphere, the particles briefly condense before the heat vaporizes them again. The process repeats endlessly in deep blue light. The color of that sky, cobalt, caused by silicate scattering, was determined spectroscopically from 64 light-years away. Astronomers examining the light of the star filtered through the planet's atmosphere as it transited across the stellar disk were able to identify the specific wavelengths absorbed and reflected. The color itself is not guesswork. The particle size that would produce that scattering profile has been calculated. What exists 64 light-years away in a sky above a world no human instrument will approach in any currently imagined future is known with enough precision to assign it a color that is worth pausing on. The cobalt blue of HD 189733b is not a metaphor, it is a measurement. Venus sits considerably closer, one of the 2 nearest planets to Earth, familiar enough to appear as the brightest object in the evening or morning sky, depending on the time of year. Its brightness is one of the most noted facts about it. What causes that brightness is a complete global cloud cover that reflects roughly 70% of all the sunlight that reaches it, and the clouds responsible are not made of water. They are concentrated droplets of sulfuric acid, layered between 45 and 70 kilometers above the surface, thick enough to hide the ground completely, and reflective enough to turn the planet into the most conspicuous object in the sky, aside from the moon and the sun. From the outside, Venus is brilliant and white and entirely opaque. From the inside, beneath those clouds, on the surface, the light that filters down is dim and orange, like the light on Earth during a dust storm, but warmer and thick with a pressure 90 times that of Earth's atmosphere, pressing down from above. The sulfuric acid in those clouds forms and dissolves in a constant cycle. Water vapor and sulfur dioxide rise from the lower atmosphere, react at altitude, and condense into droplets that hang in suspension for the duration of the cloud layer's existence. And the cloud layers, having persisted for as long as observation allows any conclusion, appears to be a permanent feature of the planet rather than a passing event. It circles Venus as Venus circles the Sun. The clouds rotate faster than the planet itself rotates, driven by winds in the upper atmosphere that complete a circuit of the globe in about 4 Earth days, even as the surface below takes 243 Earth days to complete a single rotation. What rests on the surface of Venus is simply the bottom of that cloud system, warm enough to melt lead, still enough that the rocks photographed there in the 1970s showed no erosion from wind. The sulfuric acid above the clouds is a consequence of chemistry. The temperature below them is a consequence of the clouds holding the heat in. The average surface temperature on Venus is approximately 465 degrees Celsius. This is hotter than the surface temperature of Mercury, despite the fact that Mercury is roughly twice as close to the Sun. The mechanism is the thickness of the Venusian atmosphere and its composition: carbon dioxide in enormous quantities, sulfuric acid clouds trapping radiated heat, the greenhouse process, operating at an extreme that makes the comparison with Earth's own atmospheric warming a matter of scale rather than kind. Nothing about the surface of Venus is delicate or provisional. The rocks that Venera 9 photographed in 1975 were angular and fresh-looking, uneroded, which surprised the scientists who expected billions of years of wind to have smoothed them. The surface records itself very slowly. The clouds above it change very little. The temperature, as far as any measurement can determine, has remained approximately where it is for a very long time. WASP 76 orbits its star much as HD 189733. B orbits its own, too close, too hot, locked in a synchrony that keeps one face permanently toward the star and one face permanently in darkness. But the conditions on WASP 76b carry the logic of hot Jupiter physics to a further extreme. The day side of this planet reaches temperatures that vaporize iron. Iron at those temperatures becomes a gas. It rises into the upper atmosphere, is caught in the global wind circulation, and is carried around to the night side. The night side of WASP 76b is cooler. Not cool in any ordinary sense, but cool relative to the day side. Cool enough that the iron vapor arriving from the illuminated hemisphere condenses back out of the gas phase. When iron condenses from vapor into liquid on WASP 76b, it falls. What falls is liquid iron rain. The evidence for this was gathered using the espresso spectrograph, which detected iron vapor in the absorption spectrum of the planet's atmosphere at the boundary between its day side and night side, present on one edge of the planetary disk in transit observations, absent on the other, which is exactly what the rain model predicts. The iron goes into the atmosphere as vapor on the hot side is carried around the planet as gas by winds estimated in the tens of thousands of kilometers per hour, and precipitates out on the dark side as liquid metal droplets falling through the atmosphere in the permanent night that covers half the planet. The model is consistent with the data. The rain is almost certainly liquid iron. Trying to imagine the night side of WASP 76b requires holding two things together that do not usually belong in the same image: rain, which implies something almost domestic, and iron, which implies something industrial and hard. In between, there is the fact of wind moving at roughly 18,000 kilometers per hour in darkness, at temperatures still high enough to keep most substances far above their boiling points on Earth, in an atmosphere so unlike anything that has been directly studied in detail that the comparison to familiar weather remains mostly metaphorical. The iron does not fall through air in the way rain falls through air on Earth. It falls through hydrogen and helium and traces of other gases under gravity on a planet much larger than Earth, in darkness broken only by the glow of a star that covers a substantial portion of the dayside sky. The meteorology of WASP 76b is something that exists in data and in models, and the image of iron rain has become one of the most concrete and specific results the espresso instrument has produced. What the observations of hot Jupiters like WASP 76b and HD 189733b reveal, considered together, is that the range of conditions under which weather can occur is very wide. Weather, as a process, requires a medium to carry material through, an atmosphere of some kind, and a difference in temperature or pressure between two locations. Given those conditions, material moves. The specific material, the specific temperatures and pressures, the specific geometry of how one side of a world faces a star while the other faces away, all of these determine what the weather is made of and what falls, if anything falls. On Earth, water falls through nitrogen and oxygen. On WASP 76b, iron falls through hydrogen in permanent darkness. Both are weather, in the sense that both involve materials cycling through an atmosphere under the influence of heat gradients and gravity. 55 Cancri occupies a category that has no precise equivalent in the solar system, though it belongs to a class of planets called super-Earths, larger than Earth, smaller than Neptune, rocky in composition. It orbits its star in 17.5 hours. A full year on 55 Cancri is shorter than an Earth day by more than 6 hours. The planet is tidally locked in the same way that WASP 76b is tidally locked. One hemisphere permanently facing the star, one hemisphere permanently in darkness, and the dayside surface temperature has been estimated at approximately 2,700 degrees Celsius. 2,700 degrees is above the melting point of any mineral or rock composition found on Earth. It is above the melting point of the most refractory natural materials known. At that temperature, the surface of 55 Cancri is not solid in any region exposed to its star. The leading hypothesis for the dayside surface of 55 Cancri is a global ocean of molten rock, a lava ocean covering the entire hemisphere facing the star, churning slowly under the combined effects of the tidal forces exerted by the star's gravity and the heat being deposited continuously into the surface at temperatures no known geological process on Earth produces over a sustained area. Volcanic activity on Earth produces lava in localized regions at temperatures that reach a little over 1,200 degrees in the most extreme cases. The dayside of 55 Cancri would exceed that temperature by more than twice, across an area equivalent to half the surface of a planet larger than Earth. all at once continuously. It is not a planet that would feel geological in any familiar sense. It would feel more like the interior of a furnace that happened to be spherical and orbiting a star. The term lava ocean, used in the research context, carries more precision than the image initially suggests. It does not mean a planet uniformly red and glowing in the way a volcano looks in a photograph. The surface of a lava ocean at those temperatures would emit light. It would glow across its entire visible hemisphere in the way that any very hot solid or liquid glows. The light it emits would be detectable. Some of the evidence for the surface temperature of 55 Cancri comes precisely from thermal emission measurements. From the infrared light, the day side is radiating away. The planet has been observed in transit and in secondary eclipse, meaning the star has been observed both with and without the planet in front of it, and again with and without the planet hidden behind it. And the difference in brightness tells something about what the planet itself is contributing to the total light. What the measurements say is that the day side is very hot, very radiating, and very consistent with a surface that has not solidified. The night side of 55 Cancri is less well characterized. It may be cooler, cool enough, possibly, for some silicate material to have condensed into a rocky surface in the regions permanently shielded from the star. Or the heat may be redistributed efficiently enough through the interior that the night side remains molten as well. The question of how heat moves through the interior of 55 Cancri and whether any solid surface exists anywhere on the planet is still open. Models exist, observations continue. The planet has been studied enough to produce specific temperature figures and thermal maps, but not enough to resolve every question about what the transition from the dayside lava ocean to the darker hemisphere actually looks like. Returning to the planets of the solar system for a moment, to Neptune and Uranus, where the diamonds are forming in the dark. It is worth noting how different the methods are that produce the knowledge about them, compared to the methods that produce the knowledge about 55 Cancri or WASP 76b. The planets in the outer solar system have been visited by spacecraft. Voyager 2 flew past both Uranus and Neptune, returning direct measurements of magnetic fields, atmospheric composition, and cloud structure. The diamond rain model in those planets draws on a combination of that direct observational data and the laboratory shock experiments, working from the inside and outside simultaneously. The Vinculated planets are known entirely from what their stars tell us during transits and secondary eclipses and spectroscopic analyses, light that has passed through or been emitted by these distant atmospheres, analyzed from instruments on Earth or in Earth orbit. Both approaches produce knowledge. Both leave gaps. The gaps are different. For HD 189733b, the gap is primarily in the fine structure, the detailed dynamics of the silicate clouds, the precise spatial distribution of the glass particles, the exact behavior of the wind system at different altitudes. For WASP 76b, the gap is in the nightside conditions, how the iron rain interacts with whatever lower atmosphere exists in the dark hemisphere, what the precipitation rate actually is, whether the iron accumulates somewhere or cycles continuously back around to the day side to evaporate again. For 55 Cancri, the gap is in the nightside thermal state, and the question of whether any solid surface exists anywhere. These are not gaps that suggest the findings so far are wrong. They are the kind of gaps that accumulate around the edges of things that have been partly resolved, the territory beyond what has been mapped, still open, available for the instruments that come next. The sulfuric acid clouds of Venus are, in one specific way, the most directly studied of all the extreme atmospheric features described in this section, directly studied in the sense that spacecraft have passed through them. The Venera probes descending to the surface traversed the cloud layer. Pioneer Venus probes sampled it. The composition of the clouds is known from direct measurement, not solely from spectroscopy of reflected light. The temperature profile through the cloud layer, from its top at roughly 70 kilometers altitude to its base at roughly 45 kilometers, has been measured. What lies below that level, the lower atmosphere and the surface, has been measured too. The conditions on Venus are among the best documented extreme environments in planetary science. None of this documentation makes those conditions less extreme. It simply makes them very precisely characterized. The thing about sulfuric acid clouds, as a feature of a planet's weather, is that from the perspective of the planet's total radiation balance, they are actually beneficial for the planet's continued cold, or rather for preventing any warming from reaching the surface as direct sunlight. The clouds reflect 70% of incoming solar radiation back into space, meaning that the surface of Venus receives less solar energy per square meter than the surface of Earth does, despite Venus being closer to the Sun. If the clouds were removed, the surface would receive more direct solar heating, but the greenhouse effect provided by the dense carbon dioxide atmosphere would remain, and the surface temperature would change in a complicated way, whose net result is not entirely obvious. The clouds are, in the current state of Venus's atmosphere, part of a balance that has settled over geological time. The balance involves extreme heat, extreme pressure, extreme chemistry, and a brightness visible from Earth with the naked eye. It is a stable balance in the sense that it has persisted. It does not feel stable from the inside. The Great Red Spot on Jupiter, though not a subject of this section's main thread, shares something structural with all of the weather phenomena described here, a persistence at scale that is not easy to explain by direct analogy with weather on Earth. A storm that has lasted at minimum 350 years, and possibly longer, operating at a scale that, at its historical maximum, was wider than Earth's entire diameter. This is not weather in the domestic sense that word carries in daily conversation. It is a fluid dynamic phenomenon of a gas giant, sustained by conditions that do not dissipate in the way that terrestrial storms dissipate, living on a planet with no solid surface to lose energy against. The extreme weather of the outer solar system and the exoplanets is, in this sense, simply the extension of principles that operate everywhere: fluid dynamics, thermodynamics, the movement of material from where it is abundant to where it is not, expressed in conditions and at scales that the Earth's own atmosphere does not provide room for. The silicate glass in HD 189733b's atmosphere is the same class of material as the sand on a beach on Earth. Not chemically identical, the specific silicate composition differs, but structurally related, in the same broad category of silicon and oxygen compounds that make up the bulk of Earth's crustal rocks. The fact that silicate particles can exist in a gas giant's atmosphere as suspended cloud-forming material at temperatures of around 1,000 degrees on the day side and scatter light in the blue part of the spectrum is a specific application of physics that is already well understood. The particles are acting the same way they always act. The light is scattering the same way it always scatters. The atmosphere is doing what gas under differential heating always does. Nothing about the conditions on HD 189733b violates physics. It simply applies physics to a situation that has no parallel in the solar system, and the result is glass rain in a cobalt sky. There is something worth noticing in how many of the extreme weather conditions described here involve material cycling. The diamonds in Neptune form from carbon and fall. The silicate in HD 1897333b's atmosphere condenses and evaporates and cycles back. The iron-on WASP 76b is vaporized, transported, rained out, and presumably cycles back to the day side to vaporize again. The sulfuric acid on Venus forms, exists in suspension, and may dissipate and reform in the cloud's internal chemistry. Even the lava surface of 55 Cancri A, if material is erupted from the interior and eventually carried back by convection, participates in a kind of cycle. Weather at these scales and under these conditions is not a catastrophe. It is circulation. Material moving through a system driven by heat, returning by gravity, arriving again in altered form. The violence of the individual conditions, the temperatures, the speeds, the chemical extremities sits inside a process that is in its broadest structure, ordered and repetitive. What the laboratory experiments with laser shock compression captured in the case of the Neptune diamond model was a moment, a very brief, very intense, very contained moment in which the conditions inside an ice giant were approximated in a controlled environment, and the outcome was observed. The diamonds in those experiments did not persist. They existed for the duration of the experiment, and then the conditions that produced them ended. But the data they produced, the specific pressures and temperatures at which the diamond formation transition occurred, gave planetary scientists a number to work with, a point on the phase diagram of carbon that the interior of Neptune almost certainly passes through. The diamonds inside Neptune do not come and go in the same way. They form and they fall and they accumulate somewhere in the deep interior of the planet. Over the billions of years the planet has been cycling its carbon downward through its own crushing weight. 55. Cancri E does not have billions of years in quite the same sense. Or rather, it does, but the rate of change on its surface is so high that the time scale for any given feature is very short. The lava ocean is not static. It circulates. It may erupt. It may receive material from the interior or lose material from its surface in ways that the current models have not fully characterized. But the orbit continues. The year of 17.7 hours completes, and then completes again, and then again. The day side faces the star. The star deposits its heat. The rock on the surface does not cool. The process that has been running since the planet formed continues to run. The lava ocean does not know it is being observed from 64 light-years away by instruments that detect its thermal emission. It simply maintains the temperature it is at, because the conditions that maintain that temperature are not changing. From the outside, from the perspective of an observer watching 55 Cancri transit its star, watching the secondary eclipse, analyzing the light curves, what is visible is a consistent signal. The planet transits. The brightness dips predictably. The secondary eclipse occurs. The brightness recovers. The thermal emission in the infrared corresponds to a very hot day side. All of it is consistent. All of it falls within what the lava ocean model predicts. The planet, completing its orbit in less than a day, moving through each position in its year, in the time it takes the Earth to rotate, not quite fully once, describes its path around its star with perfect mechanical regularity, while its surface churns slowly beneath the glare. Something about the specific fact that 55 Cancri completes its year in 17.7 hours settles into the imagination differently from larger orbital periods, a year that is shorter than a working day, a year that began and ended before anyone reading about the planet for the first time this evening finishes reading. The planet has completed several orbits in the time it takes to describe it. In the time it takes to describe the silicate rain on HD 189733b, to consider the iron rain on WASP 76b, to trace the diamond formation in Neptune's interior, to think through the chemistry of Venus's cloud layer, 55 Cancri Qual have completed another of its years, unremarked upon, the surface still molten, the day side still glowing in its own thermal light. The worlds described here are not exceptions to the rules of planetary science. They are what planetary science looks like when the same rules that apply to the Earth are applied to different starting conditions: more heat, more mass, closer orbits, more extreme chemistry. Diamond rain inside a gas giant is carbon under pressure. Silicate glass rain in a hot Jupiter's atmosphere is particulate matter in circulation. Iron rain on WASP 76b is a metal cycling through a phase change. The sulfuric acid clouds of Venus are an atmosphere in chemical equilibrium at high altitude. The molten surface of 55 Cancri is rock at a temperature where rock does not remain solid. None of these require unusual physics. They require the ordinary physics of heat and pressure and gravity and chemistry applied to conditions that differ from those on Earth in degree rather than in kind, and in the total darkness of Neptune's deep interior, far from the outer cloud layers that face the sun and scatter its distant light into the pale blue-green that distinguishes the planet from the star field behind it. Carbon atoms press against each other under a weight that has been accumulating for more than 4 billion years. They arrange themselves into the geometric form that carbon takes under those conditions. The form is crystalline, transparent, the hardest natural material that forms on Earth under far less extreme circumstances. The diamonds fall toward the planetary core, unhurried, through layers of compressed material that bear no resemblance to the ice the word suggests, through an interior that no instrument has measured and no spacecraft has approached. The planet continues its slow orbit far out in the solar system, presenting its calm blue-green face to any telescope pointed in its direction, giving no outward sign of what is happening in the dark below its clouds. 55 Cancri, in its own orbit far from the solar system, completes another revolution. The lava ocean on its day side turns slowly under the light of a star that fills a large fraction of its sky. The year is 17.5 hours long, and it ends the same way it began and begins again. The orbit is small and fast and precisely regular, and the surface it carries around the star does not change in any meaningful way from one pass to the next. The same temperatures, the same glow of thermal emission, the same slow circulation of molten rock that has not solidified in the time the planet has existed and shows no sign of doing so any time soon. Another year ends, another begins. The star holds the planet in its orbit. The lava holds the heat of the star against its surface, and the surface holds the heat, and another year begins. In the year 2004, on the 27th of December, instruments designed to record disturbances in Earth's ionosphere registered something that had traveled a very long way to get there. The source was a magnetar, a class of neutron star with magnetic fields so dense that describing their strength requires numbers most people have no daily equivalent for. From a distance of approximately 50,000 light-years, a pulse of gamma radiation crossed the full width of that space and arrived at the top of Earth's atmosphere with enough energy to stir the ions in the upper air into a faint and measurable response. No one on the ground felt anything. No one noticed. The disturbance was recorded afterward in instrument data by researchers who were looking for exactly that kind of signal, and what they found confirmed that a single event, far out in the galaxy, had reached all the way to the edge of the sky above this planet and left a quiet mark on the record. The magnetar responsible is cataloged as SGR 1806 to 20. It sits in a region of the Milky Way unreachable by any current instrument other than light itself, a neutron star with a magnetic field estimated somewhere between 10 trillion and a quadrillion times stronger than the magnetic field of Earth. A neutron star is already an object so dense that a single teaspoon of its material would weigh roughly as much as a mountain, the collapsed remnant of a star that burned through its fuel and then folded under its own gravity in an instant of compression. A magnetar takes that already compressed body and wraps it in a magnetic field of a scale that has no useful comparison in ordinary experience. The field is not a feature added to the object. It is part of the object's essential character, woven into its crust in ways that generate enormous internal stress, and it is that stress, the slow accumulation of magnetic tension, cracking through the star's rigid surface, that produces the flares. The December 2004 flare from SGR 1806 to 20 was the most energetic event of its kind ever recorded from a source outside the solar system. In a fraction of a second, the magnetar released more energy than the sun produces in 250,000 years. That release traveled outward in all directions at the speed of light, and at 50,000 light years of distance, what arrived at Earth was a ripple, still powerful enough to ionize the upper atmosphere, still distinguishable from background noise in the instruments designed to catch it, but attenuated by the vast scale of the journey to something that left no trace at ground level. The scientists who analyzed the ionospheric records described it as a measurable disturbance. They did not describe it as a close call. At that distance, the energy arriving at Earth was a breath of the original event, interesting precisely because it was still detectable after crossing so much space. What makes the 2004 event particularly worth noting is the kind of attention it required to notice at all. No one looked up from whatever they were doing on the 27th of December and felt anything different in the air. The sky did not change color. No instrument that any ordinary person interacts with showed any deviation. The event exists only in the careful records of scientific instruments designed to measure the specific frequency bands that gamma radiation occupies, and in the subsequent analysis of data that required researchers to work backward from a faint signature to the event that produced it. The pulse had crossed 50,000 light years, passed through the atmosphere of an inhabited world, and departed again without consequence, and the only evidence it had arrived was a line on a graph that without context would look like noise. SGR 1806 to 20 almost certainly produced other flares before and after December 2004. Magnetars are known to cycle through periods of relative quiet and periods of heightened activity, their crusts stressed and cracking under the influence of their own magnetic fields, releasing energy in bursts whose timing cannot currently be predicted. The 2004 event was recorded because it was the largest of its kind, yet measured from an extragalactic source, detectable even at the enormous distance between that magnetar and Earth. Smaller events from the same object would leave no trace in instruments monitoring Earth's ionosphere. They would simply travel outward and fade. There is another kind of star whose existence was proposed in a 1975 theoretical paper before anyone had confirmed that such an object could form at all. Kip Thorne and Anna Zitkov described what would happen if a neutron star, the same dense, compressed remnant as a magnetar, though without the extreme magnetic field, were to merge not with another neutron star, but with a red giant or red supergiant. The mechanics of such a merger involve the neutron star spiraling inward through the outer layers of the giant star over a long period, eventually settling at the center of the larger body and replacing its conventional stellar core with something far more compressed. The resulting object would look, from the outside, like an ordinary red giant. It would have a surface. It would emit light at the frequencies red giants emit. It would drift through space like any other aging star. But at its center, where a normal giant has a core of processed stellar material, carbon, oxygen, heavier elements built up through fusion over billions of years, a Thorne-Zeitkov object would have a neutron star, and the physics of energy generation in such a body would differ in subtle but detectable ways from the physics of any ordinary giant. The difference shows up in the surface chemistry because energy production in a Thorne-Zeitkov object involves processes that standard stellar fusion does not. The star's atmosphere accumulates certain elements in abundances that no ordinary giant would display. Rubidium, lithium, molybdenum, elements that a normal red supergiant produces in small quantities or not at all, would appear at the surface in concentrations that no standard stellar evolution model predicts. For nearly 4 decades after Thorne and Zeitkov published their paper, no confirmed example of such an object had been found. The model existed, the predictions existed, the evidence did not. In 2014, a team studying stars in the Small Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere as a faint smear of light, identified a red supergiant designated HV 2112, whose surface chemistry matched the predictions almost exactly. The abundances of rubidium, lithium, and molybdenum were anomalous in precisely the way a Thorne-Zeitkov object should be anomalous, and no other explanation for the pattern accounted for all 3 elements simultaneously. HV 2112 was identified as a candidate, not confirmed beyond all doubt, because the uncertainties in stellar spectroscopy are real and acknowledged, but a genuine candidate for the class of object that had been theorized for 40 years without a single known example. The paper describing the finding was careful in its language. Its authors noted that further observation and analysis would be required. What they had found was an object that looked, by one of the only methods available for testing such a thing, like exactly the kind of star the theoretical model had predicted would exist. From the outside, HV 2112 looks like a red supergiant. It sits in the sky of the Small Magellanic Cloud at a distance of roughly 200,000 light-years from Earth, too far to resolve into a disk or examine in any structural detail. What is visible is its light, spread into its component wavelengths by a spectrograph, and in those wavelengths the chemical fingerprint of its atmosphere sits slightly out of place, the signature of elements in proportions that ordinary stellar evolution by itself does not produce. The neutron star at its center, if it is there, is entirely invisible. It produces no separate signal, no detectable pulse, nothing that would betray its presence, if not for the slow leaking of its unusual physics into the chemistry of the star surrounding it. The question of why certain stars behave in ways that resist classification occupied a great deal of attention in the years following the launch of the Kepler Space Telescope, which operated from 2009 to 2018 and monitored the brightness of over 100,000 stars simultaneously, looking for the regular, predictable dips in light that signal a planet crossing in front of its host star. The data Kepler returned was vast. Analyzing it required contributions from professional researchers, automated algorithms, and eventually large groups of volunteer citizen scientists who reviewed light curves by eye to catch patterns that algorithms might miss. In 2015, that process produced something no one had been looking for. KIC 8 462852, a star in the constellation Cygnus at a distance of approximately 1400 light-years, displayed brightness dips unlike anything in the standard catalog of planetary transits. A planet crossing in front of a star produces a dip of a specific depth, a specific shape, and a specific regularity. The same planet, the same depth, the same timing, every orbit. What Kepler found in the light curve of KIC 8 462852 was none of those things. The dips were irregular in their timing. They varied in depth, including events that blocked as much as 22% of the star's light, far more than any plausible planet could account for, since a planet the size of Jupiter, the largest type known to orbit sun-like stars, would block roughly 1% of its host star's light. The dips came and went with no obvious pattern. Some were brief, some extended. The shape of each event was different from the last. The star is sometimes referred to by the nickname Tabby's star, after Tabitha Boyajian, the astronomer who led the first analysis of its unusual light curve. Boyajian and her colleagues worked through the list of explanations that might account for what Kepler had recorded, setting aside those that the data ruled out, and narrowing the field to the ones that at least partially fit. A swarm of comets drawn into the inner system after a gravitational disturbance had been proposed. Clouds of circumstellar dust in an unusual geometry had been proposed. The possibility of a disk of material left over from the collision of large bodies in the system had been considered. Each explanation accounted for some features of the observations and struggled with others. By the time follow-up observations were organized and new data gathered, including multi-wavelength monitoring that tracked how the star's brightness changed at different wavelengths during dimming events, the evidence had settled towards circumstellar dust as the most scientifically supported candidate, but the precise origin, structure, and history of that dust remained, and remains, genuinely unresolved. What is not genuinely unresolved, though it was discussed extensively in the months following the first publication of the Kepler findings, is whether the dips might have an artificial cause. The fraction of a percent of the popular coverage of KIC 8462852 that explored the possibility of artificial megastructures around the star was not a serious scientific hypothesis in the formal sense. It appeared in the literature as an exercise in ruling out the most exotic explanations before the more mundane ones, and the subsequent observations strongly constrained any such interpretation. The dimming events are wavelength dependent in exactly the way that fine dust would make them, and not in the way that a solid structure would. What Tabby's star is doing remains incompletely explained. What it is not doing has been, in that specific regard, considerably narrowed. The light curve data for KIC 8 462852, gathered over the years of Kepler's operation, occupies a relatively small place in the enormous archive the mission produced. A single unusual star among many thousands, were to its light curves standing apart from the orderly periodic signals that marked planets and the smooth, unvarying records that marked stable stars. The data is public. Researchers continue to analyze it. The star continues to behave in the way it has always behaved, dimming and brightening on its own schedule, for reasons that science has narrowed but not yet fully resolved. A different category of stellar unusual behavior involves not irregular dimming, but something closer to displacement, stars that are moving so fast they have left the gravitational system they were born in. Hypervelocity stars were first predicted theoretically in 1988, before any example had been confirmed, and they move at speeds between approximately 700 and 1,000 kilometers per second or more, which is fast enough to exceed the escape velocity of the Milky Way galaxy. An ordinary star moves through the galaxy at speeds in the range of tens to a few hundred kilometers per second. A hypervelocity star, by comparison, is traveling in a way that no gravitational structure in the galaxy can reclaim. The mechanism by which most hypervelocity stars are thought to gain their speed is called the Hills mechanism, named for the astronomer Jack Hills, who proposed it in 1988, the same year the first hypervelocity star was confirmed by observation. The scenario involves a binary star system, two stars orbiting each other in close mutual orbit, that wanders into the vicinity of Sagittarius A*, the supermassive black hole at the center of the Milky Way. The gravitational field of a black hole, 4 million times the mass of the Sun, is not uniform across the space occupied by a binary pair. The star closest to the black hole at the moment of close approach experiences a far stronger gravitational pull than the star on the far side. The pair is disrupted by this differential. The tidal force across their separation is stronger than the force binding them to each other. One star is captured by the black hole's gravity, entering a close orbit around it. The other is released at enormous speed, carrying the momentum of the original binary orbit, amplified by the extreme gravity it passed through, and it departs along a trajectory that takes it out of the galactic center at a velocity no other force in the galaxy can match. The star that leaves does not know it has a companion behind it. Stars do not have knowledge of anything, but the physical picture that emerges from the mechanics is one of separation, a binary pair that had orbited together, perhaps for billions of years, drawn apart by a gravitational encounter neither star's fate could have been predicted from at any earlier point in their history. One remains near the center of the galaxy, likely in a tight modified orbit around the black hole. The other travels outward, through the galactic disk, through the outer halo, eventually into the intergalactic space that separates the Milky Way from its nearest neighbors. The journey takes millions of years. By the time a hypervelocity star reaches the outer halo, the galactic center it came from is millions of light years behind it, visible only as part of the faint glow of the galaxy as a whole. There is no drama in this process from the star's perspective, because a star has no perspective. It is a sphere of plasma held together by gravity, generating energy through nuclear fusion, moving through space on the trajectory it was given by a gravitational encounter in the galactic center some number of millions of years ago. That trajectory carries it onward indefinitely, not toward any particular destination, but simply outward, in the direction it was launched, at the speed it was given. The Milky Way's gravity will eventually fail to slow it enough to bring it back. It will cross the boundary of the galaxy and continue into the space between galaxies, traveling through a region so empty that the nearest star of any kind will be thousands of light years away, then tens of thousands, then more, the galaxy becoming, over millions of years, only a structure visible behind it. The stars in this category that have been confirmed are relatively few. Identifying a hypervelocity star requires measuring its speed accurately enough to distinguish it from the ordinary distribution of stellar velocities across the galaxy, and doing so for stars that may be hundreds of thousands of light years away. The first confirmed example was identified in 2005 by Warren Brown and colleagues, a blue main sequence star designated SDSS J09 0745 0 plus 02 4507, moving at roughly 850 kilometers per second relative to the galactic center. Since then, additional examples have been cataloged and the distribution of their directions of travel and their estimated ages has been used to reconstruct the probable circumstances of their ejection, which stars from which binary pairs, at which moment in their approach to Sagittarius A, asterisk, left the galactic center on trajectories that happened to align them with the region of sky where subsequent surveys found them. The galactic center itself produces other effects worth noting, but the specific signature of a hypervelocity star, an ordinary star moving at a speed that marks it, unmistakably, as something that has passed through the most gravitationally extreme environment in the galaxy, is one of the quieter and more legible records of what happens near a supermassive black hole. The star carries no physical change from the encounter. It does not look different from any other star of its spectral type, only its speed distinguishes it. In a survey that does not include velocity measurements, it would be invisible as anything other than an ordinary background star. Among the things that are not stars, even when they might be, WISE 1828 plus 2650 occupies an unusual position. Discovered in 2011, using data from the Wide Field Infrared Survey Explorer, it belongs to a class of objects called white dwarf brown dwarfs, a category so recently confirmed that the full range of its properties is still being established. Brown dwarfs occupy the space between the most massive planets and the least massive stars. They form the way stars form, from the gravitational collapse of a cloud of gas and dust, but they do not accumulate enough mass for hydrogen fusion to ignite in their cores and sustain itself. They are, in the standard description, failed stars. Though the phrase implies a kind of aspiration, the physics does not actually include. They are simply objects that formed below the mass threshold for sustained stellar ignition. White dwarf brown dwarfs are the coldest known class of brown dwarf, and WISE 1828 plus 2650 is among the coldest of those. Its surface temperature is estimated at approximately 300 Kelvin. To place that number in context, 300 Kelvin is approximately 27 degrees Celsius, roughly the temperature of a warm room, or the surface temperature of the human body. A star like the Sun has a surface temperature of approximately 5,800 Kelvin. The outer planets of the solar system have surface temperatures in the range of 100 to 200 Kelvin. WISE 1828 plus 2650, a stellar class object formed from the gravitational collapse of a gas cloud, has a surface warmer than Uranus and Neptune, but cooler than the equatorial surface of Mars. At that temperature, an atmosphere composed of the gases that brown dwarfs accumulate during formation, hydrogen, helium, methane, ammonia, water vapor, would exist in a state in which water could form liquid droplets, or possibly ice crystals, depending on local pressure and the vertical structure of the atmosphere. Researchers studying the properties of white dwarf atmospheres have proposed that objects in this temperature range might host cloud layers composed of water, not sulfuric acid clouds, not silicate clouds, but water clouds of the kind more commonly associated with planets in a habitable zone, forming and dissipating in the cold upper atmosphere of an object that is by origin a star. The observations required to confirm the presence of such clouds are at the edge of what current instruments can detect for an object so faint at such a distance. The theoretical case for their existence rests on atmospheric models that have been calibrated against the spectral signatures of warmer brown dwarfs and extrapolated into the white dwarf regime, where the models become harder to test directly. What WISE 1828 plus 2650 looks like in ordinary visible light is nothing. It emits essentially no optical light. The human eye, or any camera sensitive to the wavelengths of light that stars typically emit in visible quantities, would find nothing at its location in the sky. The survey that discovered it operated in the infrared, wavelengths longer than visible light, associated with heat rather than with the nuclear energy output of ordinary stars. In that part of the spectrum, WISE 1828 plus 2650 appears as a dim point, its faint warmth distinguishable from the background with careful analysis, its spectrum revealing the chemical signatures of its atmosphere and absorption, features that require a detailed comparison with theoretical models to interpret. Its distance from the solar system is estimated at somewhere between 40 and 50 light years, which places it in what astronomers casually refer to as the solar neighborhood, the local region of the galaxy in which most well-studied stars reside. In this neighborhood, it floats, entirely dark to most instruments, radiating heat at a level that could, on a cold night, be matched by a domestic radiator. Nothing about it is visible to the eye. Its presence in the catalog of known objects rests entirely on the infrared survey that swept this region of the sky and the subsequent spectral analysis that distinguished its emissions from the background. There are likely other objects of its class and colder classes below it, if any exist, in the space between the Sun and its nearest stellar neighbors, not yet discovered because no survey has yet covered that region of the sky at sufficient depth in the relevant infrared bands. The census of objects in the solar neighborhood is ongoing and incomplete. WISE 1828 plus 2650 is an example of the kind of thing that becomes visible only when the right instrument is pointed in the right direction, and whose existence says something not just about brown dwarfs, but about how much of the sky remains, in practical terms, unmapped at the relevant wavelengths. The warmth it releases has been traveling outward since the object formed, some billions of years ago, in the slow gravitational contraction of a cloud of gas that did not quite have enough mass to become a star. That warmth has been crossing the dark between it and every other object in its vicinity at the speed of light, a continuous emission so faint that it is distinguishable from the cosmic background only with instruments designed specifically for that purpose. If WISE 1828 plus 2650 has water clouds in its upper atmosphere, those clouds have been forming and dispersing in the cold layers of its atmosphere for as long as the object has existed. No one present to observe them, no instrument yet trained on their specific altitude and composition with sufficient resolution to confirm them, just pale water vapor condensing in the dark above a failed star that glows only in wavelengths the eye cannot see. The magnetar sends its flares across the galaxy, and some fraction of them arrive at planets. The merged object in the small Magellanic Cloud drifts through its host galaxy with a neutron star at its center, its unusual surface chemistry, readable only in the spread of its light across a spectrograph. Tabby's star dims and recovers on its own schedule, its circumstellar dust moving through its system in a geometry that has not yet been fully reconstructed. The hypervelocity stars that left the galactic center millions of years ago continue outward toward the intergalactic space. They will reach in millions more, carrying no memory of the binary companions they were separated from, carrying only the speed they were given in a moment of gravitational disruption near a black hole 4 million times the mass of the Sun, and somewhere in the solar neighborhood, close enough that light from it would take only 40 to 50 years to cross to Earth. WISE 1828 plus 2650 drifts in the infrared dark, a little warmer than the space around it, a little cooler than almost anything else that formed the way it did. Its possible water clouds, if they exist, rise and fall in its upper atmosphere in cycles governed by the same physics that governs clouds on worlds with much larger suns. No one has yet seen them. The instruments that might confirm them are either not yet built or not yet trained on that specific region of the sky at that specific time. For now, WISE 1828 plus 2650 exists in the catalog as a spectral fingerprint, a temperature estimate, and a question about what its atmosphere holds, a faint and quiet object, still giving off its warmth into the space around it, in a neighborhood whose full census has not yet been taken, carrying its possible water clouds through the cold, unhurried dark, just barely visible to the instruments designed to find it, and entirely invisible to everything else. At approximately 48 astronomical units from the Sun, in the cold and mostly empty outer reaches of the solar system, the count of objects simply drops, not gradually, not in the slow thinning that might be expected as the Sun's influence grows more distant and the original material of the solar system grows sparse. The count drops sharply, at a boundary that sits roughly where the Kuiper belt should still be dense with objects, and then there is noticeably less of everything than the models say there ought to be. No single telescope image shows this. No photograph captures the edge. It appears only in data, in the careful cataloging of thousands of objects at known distances, the tally running along at its expected rate, and then at that particular distance, falling away. The gap has a name. It is called the Kuiper Cliff. What makes the Kuiper Cliff worth sitting with is not the drop itself, but what the drop implies. Standard models of how the solar system formed and settled into its current arrangement do not predict a boundary there. The outer Kuiper belt, in those models, should thin gradually over a much wider range of distances, not cut off as cleanly as it appears to do. Something altered the distribution of objects in the outer solar system, and that something has not yet been confidently identified. One proposed explanation involves a large planetary body sitting beyond the belt, a world massive enough to have gravitationally perturbed the region, clearing or scattering objects in a pattern that would produce exactly the kind of cliff the data shows. The proposed body has not been found. It may exist, and the search for it continues in the survey data of every wide-field telescope currently operating. It may turn out to have a different explanation entirely. The outer solar system has a way of producing these quiet, data-only anomalies, features that do not announce themselves in photographs, but appear when enough patient counting is done. There is no dramatic visual. There is a line of numbers, and then a shorter line of numbers, and the place where the change happens is a question the solar system has not yet answered. For now, the Kuiper Cliff sits at the edge of what has been cataloged and mapped, the outer edge of the census, a drop in the count of small worlds at a place no model quite expected. Moving inward through the solar system, past the belt of outer objects, and through the gas giant's wide orbits, there is something sitting at the top of Saturn that rewards looking at for a long time. It is a hexagon, not a rough approximation of one, not a six-sided shape that requires some interpretive generosity to recognize, a precise geometric hexagon, approximately 30,000 kilometers across, each of its 6 sides longer than the full diameter of Earth, rotating at the top of a gas giant as though someone had drawn it with careful instruments. The Voyager spacecraft photographed it in 1981. The Cassini spacecraft, orbiting Saturn decades later, photographed it again in high resolution and found it unchanged. The same shape, the same location, the same wind-driven rotation it had always had. The hexagon is a feature of Saturn's jet stream. At the altitude where the pattern forms, a band of air moves at approximately 320 kilometers per hour, and the interaction between that fast-moving band and the atmospheric layers around it produces a standing wave, a wave that, at Saturn's particular combination of rotation rate and fluid dynamics, settles into 6 sides rather than 5 or 7, or the smooth circular form one might expect. This is reproducible in a laboratory. Rotating cylinders of water, spun at different rates in their inner and outer regions, produce the same polygon shapes depending on the speed differential involved. The number of sides the pattern develops turns out to be predictable from the physics. What is harder to hold is that this mathematics worked out in a cylinder of water on a workbench describes something 30,000 kilometers wide, floating at the top of a world 8 times larger than Earth. The Cassini mission photographed the hexagon in different seasons, different lighting conditions, different spectral bands, and the shape remained consistent across all of them. Precisely 6 sides, each side a gentle arc rather than a perfectly straight line, which is itself a consequence of the wave dynamics involved. Inside the hexagon, a large cyclonic vortex sits at the pole, a separate feature from the hexagonal jet stream itself, the two rotating at slightly different rates. The hexagon turns, the inner vortex turns, Saturn turns beneath both of them on its 10-7-hour day. The whole arrangement has been there, at least since 1981, and probably far longer, a standing geometric feature of an atmosphere in which no solid surface exists to anchor it. There are things in the solar system that have been changing within the span of human observation, and Jupiter's Great Red Spot is one of the clearer examples. When late 19th century astronomers trained their instruments on Jupiter and sketched the broad features of its cloud bands, the Great Red Spot was large enough to hold several Earths across its width. Estimates of its historical size vary, but a span of approximately 40,000 kilometers is broadly consistent with old drawings and early photographs. By the time detailed photographic records began to be compared systematically, it was already smaller. Each decade brought a smaller storm, not so much smaller that it seemed urgent at any one moment, but in the long record of comparison, it became clear that the Great Red Spot was not stable. It was shrinking. The storm itself is an anticyclone, a high-pressure system that rotates in the opposite direction from cyclones, drawing material inward in a slow and steady rotation that has been continuous for at least 350 years of human observation. What drives a storm to persist for that long is still not entirely understood. The leading hypothesis involves the storm sustaining itself by absorbing smaller storms that drift into it from the surrounding cloud bands, pulling their energy into its own circulation. Smaller vortices observed near the edge of the red spot appear to merge with it periodically, and some researchers have proposed that this merging process is what keeps it going. The shrinkage observed in recent decades may reflect a change in how available those smaller feeding storms are, or it may reflect something else about the dynamics of the cloud layers at that latitude. The measurements are consistent. The rate of shrinkage appears to have increased in more recent observations. The storm still exists. At approximately 16,350 kilometers across by 2017, it remains the largest active storm in the solar system, smaller than it was, still spinning, still clearly visible as a reddish oval against the lighter cloud bands surrounding it. Something in the longer view of this is worth slowing down on. A storm that has persisted for centuries is still, in terms of the solar system's history, an extremely young feature. Jupiter is approximately 4-5 billion years old. The Great Red Spot, even if it has been continuous since the very first telescopic observations, has existed for an almost invisibly small fraction of that history. Whether it persists for another century or gradually dissipates over the next few decades, its presence in the record of human planetary observation will have been a brief thing. The photographs from the 1800s show it wider. The photographs from the 2020s show it narrower. Somewhere in that progression is a storm conducting its entire lifetime within the span of recorded history, ordinary in scale relative to the planet's age and remarkable in its persistence relative to anything on Earth. At 887 million kilometers from the Sun, on average, Saturn carries its rings and its hexagon and its dozens of moons in a wide, slow orbit that takes approximately 29 Earth years to complete. Among those moons is one that warrants particular attention. Enceladus is small, approximately 500 kilometers in diameter, which is roughly the distance from one end of a medium-sized country to the other, gathered into a sphere. Its surface is almost entirely white, one of the most reflective surfaces in the solar system, because it is covered in fresh ice. The ice is fresh because Enceladus is constantly renewing it. Near the moon's south pole, where four long parallel fractures run across the icy crust, material from the interior vents continuously into space. The plumes emerging from those fractures contain water vapor, ice crystals, molecular hydrogen, organic compounds, and silica nanoparticles. The molecular hydrogen is particularly significant. It indicates that somewhere in the interior, hot water is in contact with rock, a chemical interaction called hydrothermal activity that on Earth provides the energy and chemistry for entire ecosystems that receive no sunlight at all. The silica nanoparticles point toward water temperatures of at least 90 degrees Celsius at the point of contact with the seafloor. Together, these components form a picture of a subsurface ocean kept liquid by tidal heating, the gravitational flexing that Saturn's enormous mass produces in Enceladus as the moon moves through its slightly elliptical orbit, generating friction and warmth deep in the interior. The ocean is global. It sits beneath the icy crust across the entire moon, touching a rocky seafloor below, and in places near the South Pole, it communicates directly with the surface through those fractures. What the plumes make possible is direct sampling. The Cassini spacecraft flew through the plume material on multiple occasions and measured its chemistry without needing to land or drill. The organic compounds detected include some of the simpler building block molecules involved in the chemistry of life as it exists on Earth. This does not mean life exists in the ocean beneath Enceladus's ice. It means the environment contains some of what would be needed, and that the material escapes naturally in a form that can be measured from orbit. The ocean is warm, chemically active, and has probably existed for long enough that the slow processes of chemistry have had time to work. What those processes have produced is an open question, and it is likely to remain one until a more capable mission is sent. The plumes rise from the South Pole, stream outward into the space around Saturn, and contribute material to Saturn's outermost ring, the E-ring, a diffuse and wide band of fine ice particles that Enceladus continuously replenishes as it orbits. Stand far enough back from Saturn in the imagination, and Enceladus is visible as a tiny bright point moving along its orbit, trailing the faintest possible contribution to a ring structure millions of kilometers wide. The plumes themselves, caught in backlit images from Cassini, appear as bright curved streaks rising from the small white moon, water ascending from a warm ocean into the cold dark above, some of it falling back to the surface, some of it escaping into the ring system, some of it sampled and measured by a spacecraft that spent 13 years in Saturn's neighborhood before its mission ended. It is worth moving for a moment to the innermost planet, where a different kind of surface feature was waiting for a spacecraft patient enough to map it. Mercury sits close enough to the Sun that the light arriving at its surface is approximately 7 times more intense than the light arriving at Earth's surface. Its days are long. A solar day on Mercury lasts approximately 176 Earth days, and the surface exposed to that sustained intensity has had time to develop features unlike anything on other rocky worlds. The Messenger spacecraft, which orbited Mercury between 2011 and 2015, identified thousands of small, shallow depressions scattered across the surface. They are bright against the surrounding terrain. Their edges are sharp. The material around them appears freshly exposed, not darkened or mixed with the older surface material the way eroded features normally are. These are called hollows. The leading explanation for how hollows form involves a process called sublimation, the direct transition of a solid material to vapor without passing through a liquid phase. Mercury's surface contains volatile compounds, materials that at moderate temperatures would slowly convert to gas. Under the sustained direct radiation of a nearby sun, with no atmosphere to speak of, and no protection from the full spectrum of solar output, patches of surface material containing these volatiles may simply convert upward, the volatile component departing as vapor through the exosphere, leaving behind a shallow bright depression with clean edges where the surrounding material has not yet been disturbed. The process is thought to be ongoing. The fresh appearance of the material around hollows suggests they are still forming, still slowly growing in some cases, still releasing their volatile content into a thin exosphere that gradually carries it away. What makes hollows interesting beyond their formation mechanism is what they reveal about Mercury's composition. The presence of volatile compounds on the surface of the innermost planet, where the solar environment is most hostile to their preservation, was not predicted with confidence before Messenger arrived. Mercury was expected to be a relatively depleted, heavily baked world, stripped of volatiles by its proximity to the Sun and the intense early solar activity of the solar system's first billion years. The hollows complicate that picture. They suggest either that volatile compounds have been delivered to Mercury's surface more recently than expected, or that they have been preserved in ways not yet fully understood, or that Mercury's early history was somewhat different from the models that predicted their absence. The hollows are still being studied. Their full distribution across the surface is mapped. The exact chemistry driving them is still being worked out from the spectral data Messenger returned before its mission ended. Saturn's hexagon, Jupiter's shrinking storm, Enceladus's plumes, Mercury's bright hollows. Each of these is a feature of a world in the same solar system whose outer edge appears to drop away unexpectedly at 48 astronomical units. They are all neighbors, cosmically speaking. They are all products of the same original cloud of gas and dust that collapsed 4-5 billion years ago, settled into a rotating disk, and gradually assembled itself into planets, moons, rings, and smaller bodies through collisions and accretion and gravitational sorting. What they share is an origin. What they reveal is how differently the same starting conditions can develop when they play out across different distances from a central star, different sizes of body, different compositions, different orbital circumstances. The outer solar system has its cliff in the data. Saturn has its hexagon and its small, warm ocean moon. Jupiter carries its long, shrinking storm in its southern hemisphere cloud bands. Mercury keeps its bright, freshly forming depressions close to a sun that is not done working on the surface. Every one of these is a solar system feature that has been detected and measured, not speculation, not theoretical prediction awaiting confirmation, but something a spacecraft has looked at, or a telescope has mapped in enough detail that a name has been given to it and papers have been written. The solar system is in this sense not a finished object. It is an ongoing set of processes, some of them producing features that were not expected, some of them changing in ways that can be tracked across human timescales, some of them posing questions that the instruments of one generation answer, partially enough that the next generation builds better instruments. What the data on the Kuiper Cliff does not yet contain is a confirmed cause. The sharp drop in object density at 48 astronomical units sits in the survey records as a measured feature of the outer solar system, consistently observed, consistently inconsistent with the simplest formation models. The proposed large planetary body beyond the belt is one explanation among several. The gravitational influence of an early close stellar encounter during the solar system's formation is another. A combination of factors operating at different times is another. None of these has been confirmed, and none has been ruled out, which puts the Kuiper Cliff in the same category as several other solar system features, whose outlines are clear and whose explanations are still being debated among researchers with access to the same data. There is something worth sitting with in that. The solar system has been studied with systematic instruments for more than a century, mapped with spacecraft for more than 60 years, and cataloged in increasing detail through every decade of that period. The broad outlines have been known for a long time. The 8 planets, their approximate sizes and compositions, the structure of the asteroid belt, the existence of the Kuiper belt, and the Oort cloud beyond it, these are not new discoveries. What has emerged from closer attention is a set of smaller, quieter questions that the broad outlines did not reveal, features and anomalies and measurements that require explanation and have not yet received complete ones. The hexagon at Saturn's pole was there when Voyager flew past. The data on Jupiter's shrinking storm has been accumulating since anyone thought to keep careful photographic records. The hollows on Mercury were waiting for a spacecraft patient enough to orbit and map. The Kuiper Cliff has been in the survey data since enough outer solar system objects were cataloged for the drop to become visible. None of this requires anything dramatic to explain. Hexagons form in rotating fluid at specific speed differentials, which is why a laboratory cylinder and a gas giant produce the same shape. Storms dissipate over time when the conditions feeding them change, which is why the Great Red Spot's gradual shrinkage is consistent with what is known about large anticyclones in general. Tidal heating keeps the interior of a small moon liquid despite its distance from the sun, which is why Enceladus has a warm ocean when a moon that size at that distance might otherwise be frozen solid all the way through. Volatile compounds sublimate when exposed to intense radiation, which is why Mercury has bright, fresh-edged depressions forming slowly across its surface. The physics in each case is coherent. What takes time is working out exactly how the physics applies in each specific environment, with each specific composition, under the specific history that produced the feature being studied. Saturn is visible from Earth with the naked eye as a pale yellowish point of light in the night sky, indistinguishable to the unaided eye from a moderately bright star. In a small telescope, the rings become visible, and with a slightly better telescope, the gap in the rings is visible as a dark line. The hexagon at the North Pole is not visible from Earth-based instruments in any practical sense. Neither are the plumes of Enceladus under normal observation conditions. These are features whose existence required sending something out there to look. Years of planning and assembly and launch, years of transit, years of orbital operation, the patience of spacecraft engineers and planetary scientists across entire careers. The gap at the Kuiper Belt's outer edge required cataloging hundreds of thousands of objects with wide-field survey telescopes over years of observation. The hollows on Mercury required an orbital spacecraft with a spectrometer and enough resolution in its imaging system to distinguish freshly exposed surface material from old. Every feature of the solar system that is known in detail is known because someone decided to look carefully, built something capable of looking, and waited. The waiting is perhaps the part that does not translate easily into the summary version of solar system science. The Cassini spacecraft spent 13 years orbiting Saturn. The Messenger spacecraft spent more than 4 years orbiting Mercury. The surveys that produced the Kuiper Belt census have been running for decades. The photographs of Jupiter that reveal the Great Red Spot's historical size extend back into the 1800s, preserved in archival collections where researchers found them and measured them and compared them with modern imaging. The solar system's details accumulate slowly through sustained attention. What is known now is considerably more than what was known 50 years ago, and there is every reason to expect that what will be known 50 years from now will be considerably more than what is known now. Enceladus continues to vent. The plumes rise from the South Pole in the same 4 fracture zones they always have, sending water vapor and organic material into the space around Saturn, contributing to the E-ring, condensing as frost that falls back onto the surface and keeps it white and reflective. The ocean beneath the ice continues to be kept warm by the tidal flexing of Saturn's gravity. The hydrothermal activity at the sea floor continues to introduce chemical energy into the water above it. Whatever processes the water chemistry has been conducting for however long the ocean has existed, millions or billions of years, the estimates vary. Those processes continue in the same warm dark below the ice, below the venting fractures, below the plumes rising into the cold above. The south pole of Enceladus, if seen from directly above at the right moment in Cassini's archive of images, shows the 4 parallel fractures called tiger stripes, each approximately 130 kilometers long, glowing faintly in the infrared with warmth escaping from below, and rising from them the plumes, not a dramatic eruption, but a steady, continuous, quiet venting, the faintest possible structural feature of a small white moon drifting in Saturn's wide ring system. In the foreground of some of those images, Saturn itself occupies part of the frame, the rings visible as pale bands, the planet behind them a pale tan sphere, many times the size of the small moon in the foreground. Enceladus, in those images, looks like something that should not be interesting. It is smooth, white, small, geometrically unremarkable from the outside. The interesting part is underneath, invisible in the optical images, accessible only through the chemistry of what rises from the fractures and what the spectrometers found in it. The plumes are still rising now, not in any visible sense from Earth. They are far too faint and far too distant for any ground-based instrument to detect directly. But from the data Cassini gathered and returned, from the models built to describe what was measured, the picture is consistent. The fractures are still open, the tidal flexing is still ongoing, the ocean below is still warm, and the material is still venting. Enceladus is mid-orbit around Saturn, as it always is, completing one circuit every 32. 9 hours, the plumes trailing from the South Pole, in the pattern they have held for as long as anyone has been close enough to see. The solar system in this way is not a static arrangement of objects whose properties have been cataloged and filed. It is a collection of ongoing processes, storms persisting and slowly changing, moons venting oceans into space, geometric features rotating steadily at the tops of gas giants, objects counting off their presence in survey data and then dropping away at distances that need explaining, and volatile compounds sublimating slowly from a surface too close to a hot star for anyone's models to have predicted they would still be there. All of it is happening continuously at this moment in the same patch of space that contains the Earth, the same patch of space that contains all of recorded human history, all the observations and measurements and waiting that produce the knowledge being described. As the Kuiper Cliff sits at its 48 astronomical unit boundary, with no confirmed cause and a catalog of objects on both sides of it. Saturn holds its hexagon at the North Pole, the same shape it was decades ago. The Great Red Spot is a little smaller than it was last year. On Mercury, somewhere in the sustained glare of a very close sun, another hollow is forming, slowly, as volatile material rises from the surface and drifts out through the thin exosphere. Enceladus arcs through its orbit, the South Pole venting quietly, the warm ocean sitting below the ice in the dark, the tidal forces of Saturn working continuously on the rock and water of the interior, keeping it all moving, keeping it all warm, keeping the plumes rising into the cold space above. There is a particular quality to the knowledge that ordinary-seeming things have remarkable interiors. A small white moon that looks smooth and unremarkable from outside holds a warm saltwater ocean and a chemically active seafloor, and sends the evidence of both of these things out through fractures in its ice into space where instruments can sample it. A gas giant that looks in a small telescope like a plain yellowish disk has at its north pole a hexagonal wave structure wider than the whole Earth and powered by physics reproducible in a laboratory. The innermost rocky planet, sun-baked and apparently simple, has a surface in the process of slowly dissolving from below in patches, leaving bright, clean-edged depressions that mark where material used to be. The outer edge of the solar system's belt of small objects is a question someone is still working on answering. The solar system is in this sense still being understood. Not in the broad strokes, those have been settled for some time, but in the quiet details that emerge from close and patient attention. The hexagon was found by a passing spacecraft in 1981, and it took another 25 years of orbital observation to map it in detail. The Kuiper Cliff became visible only when the catalogs grew large enough for the drop to stand out clearly from the expected distribution. The hollows on Mercury were wading through the entire history of ground-based planetary observation for an orbiting spacecraft with the right instruments. Enceladus's ocean was suspected after Voyager observed the E-ring being replenished, confirmed more fully by Cassini's direct measurements of plume chemistry decades later. Each discovery arrived at the moment when the instruments were good enough and the patience was long enough, and someone was paying careful attention to what the data said.